everyone. To continue with our lecture series on stereochemistry, today we will talk about the conformational analysis of cyclohexanes. As an example, we will be discussing the different conformations of a cyclohexane ring. Now, when we talk about these cyclic molecules, the first thing that comes to our mind is that whether these rings or cyclic molecules, they are planar or non-planar. So the smallest ring that you can have is a ring with 3 carbon atoms, or a 3-membered ring. So usually that is a planar ring. A planar ring means that all the carbon atoms or all the atoms in that ring are in one plane. But when we move on to higher rings with more than 3 carbon atoms in the ring, like 4-membered rings or 5-membered rings or 6-membered rings or higher rings, then the atoms within that ring are not in one plane. Or we say that the molecules with higher number of carbon atoms in the ring are non-planar. Now, why is this so? You see, when we have a 3-membered ring, so to connect all the 3 carbon atoms in that ring, the angle, the bond angle between inside that ring has to come down from a normal tetrahedral angle. So in a 3-membered ring, the angle within the ring is 60 degrees. So that is a very huge deviation from a normal tetrahedral angle when the angle comes down to 60 degrees. So it means that the molecule has to adjust itself to form that 3-membered ring, and to do so it goes away from the normal tetrahedral angle. And we say that when we have a 109.5 degrees angle, the atoms are at maximum distance from each other, so it's quite stable. But when the angle comes down to 60 degrees in a 3-membered ring, it means that some sort of stability is then associated with that molecule. And then we have 4-membered rings with like a cyclobutane ring, which has a 90 degrees angle inside the ring. A 5-membered ring, a cyclopentane ring, has about 108 degrees angle within the ring. And then we have a 6-membered ring, the cyclohexane ring, having a 120 degrees angle inside the ring. Now, as the angle deviates from a normal tetrahedral angle, it brings instability to the system, and that instability is because of a strain that is developed, which we call the angle strain. We will not talk about that in detail today. We'll talk about it some other time, but just to let you know why these rings are non-planar is because of the ring strain that is associated with these molecules. To relieve that strain to some extent, the atoms in the ring, they go out of plane. They're not in one plane, and that is why these molecules or these rings are non-planar. So we will be talking about cyclohexane today because that is one of the most important rings in most of the organic molecules. It occurs in most of the molecules, whether they are natural or even synthetic, or it is easily formed. It doesn't mean that rings other than the 6-membered rings are not present in these molecules. They are, but it usually is the most important one. And the other main reason is that the conformations of this cyclohexane ring are relatively easier to study than other rings. Now, initially, planar structure was suggested for this for all these rings, especially the cyclohexane ring, and this was suggested by Bayer, and he presented his famous Bayer strain theory, which was later challenged by Sakshi, and he said that the rings are not planar, and these were also confirmed by certain experimental procedures, which we will be talking about some other time, not today, about the Bayer strain theory and why it was challenged and how people came to know that these rings are not planar. So in a planar cyclohexane ring, all the atoms would be in one plane, but it's not so. So later it was suggested that this cyclohexane ring occurs in a non-planar form and that looks like a chair. So this is a chair form of cyclohexane. Why it's called a chair form? Because if you look at this structure, you would see that it looks like a chair, just like a chair has a back. So you see this is the back of the chair, and then it has a seat. So these two carbons here and two carbons here, they form the seat of this chair, and then this CH2 here, it forms the legs of the chair. So it looks like a chair form, chair, and that is why we say that it's the chair form of cyclohexane. Now cyclohexane has 6 carbon atoms and each carbon has 2 hydrogens attached, so the molecular formula is C6H12. So it has 12 hydrogens attached to these 6 carbon atoms, each having 2 hydrogen atoms. But when you draw it in the form of a chair, these 12 hydrogens are not equivalent in a sense. Why? Because of their orientation. You know that each of these carbon atoms is sp3 hybridized, so it would tend to have a tetrahedral geometry around it. If not exactly tetrahedral, but it would still try to orient all the hydrogens in a way that it's closer to a tetrahedral structure. So these 12 hydrogens are divided into two types or classes. 6 of them are known as the axial hydrogens, and the rest of the 6 are known as equatorial hydrogens. And I have mentioned these hydrogens with the letter A and E just to let you know that this HA means that it's an axial hydrogen, this is an axial hydrogen, this is an axial hydrogen, and the hydrogens with E mean that they are equatorial hydrogens. Now, why we say they are axial or equatorial is just because of a simple fact that if you consider this as the plane of this cyclohexane ring and you pass an axis right through the center of this molecule, you would see that 6 of these hydrogens are parallel or anti-parallel to this axis. So you pass an axis right through the ring and you see this hydrogen, this one, and these 3 hydrogens, they are parallel to this axis, while the rest of the 6 are not parallel to the axis, but they are like oriented towards the equator, or they are oriented equatorially to the plane of this chair form of cyclohexane. So that is why we call them as equatorial hydrogens. Now, chemically, you would think that they are all equivalent, but we can differentiate between them through some experimental procedures. Like, for example, we can differentiate them in NMR. Again, we will talk about that some other time when we will be discussing NMR spectroscopy. But today, I just want to let you know that these 12 hydrogens are divided into 2 types. 6 are axial and 6 are equatorially oriented. Now, how to draw this cyclohexane chair and how to draw the hydrogens with correct orientation on all these carbon atoms. So you draw a chair like this, and then you start off with one of the carbon atoms. So you know that all the axial hydrogens will be oriented axially or vertically, either vertically up above this ring or vertically down below the ring, right? So you start off with one of the carbon atoms and you draw an axial hydrogen vertically up here. So when you start off with this carbon atom, the axial hydrogen will be straight up. Now, the axial hydrogens on the adjacent carbon atom. So this is an adjacent carbon to this first carbon, and this is also an adjacent carbon to the first carbon atom. So on the adjacent carbon atoms, you will draw the axial hydrogens in the opposite direction. So if this was pointing vertically up, these two hydrogens on the two adjacent carbon atoms will be oriented vertically down. So these two hydrogens are axial and they are oriented vertically downwards. And then on the adjacent carbon atoms, we will have axial hydrogens pointing up or oriented vertically upwards. And then on the last carbon atom, we will have the axial hydrogen down. So now you see that on adjacent carbon atoms, the orientation of these axial hydrogens is opposite, or you can say that they are trans to each other. This is pointing up, and the hydrogen, the axial hydrogen on the adjacent carbon atom is pointing down. And then you move to the next carbon, it is up, this is down, and this is up, and this is down. So this is how you draw the axial hydrogens. Now we come to the equatorial hydrogens, how you draw them. So first you have to keep in mind that you have to draw a structure closer to the tetrahedral geometry. So we have the axial hydrogen pointing up here on this carbon atom. We have the two bonds here. So we have to draw another bond so as to have a geometry closer to the tetrahedral geometry. So we draw the equatorial hydrogen in this way. So it's slightly tilted downwards or oriented or pointing downwards on this carbon atom. You can take it in this sense that the axial hydrogen on this carbon is pointing up, so the equatorial will be slightly oriented downwards. And then on the adjacent carbon atom, because the axial hydrogen is pointing down or it is vertically oriented downwards, this equatorial hydrogen will be slightly pointing up, right? So again, the adjacent carbon atom has an axial pointing up, so the equatorial will be oriented downwards. Then here we have the axial down, the equatorial is slightly pointing up. Here we have the axial pointing up, and this is equatorial, so it is oriented slightly downwards. And here again we have the axial hydrogen pointing down and the equatorial is slightly up. So this is how you draw the hydrogens on this chair form of cyclohexane. So you have to practice it to learn how to draw the correct cyclohexane chair, and it's very important. It's very important in terms of stereochemistry also, and when you're dealing with such type of molecules or such type of rings in chemical reactions, considering their stereochemistries. So it's very important to learn how to draw the correct chair form of cyclohexane with all the groups or all the hydrogens oriented in the correct direction or orientation. So we have a chair form of cyclohexane, which is quite stable, as we say. But this is not the only form in which cyclohexane can occur. This chair form can flip into another chair form. So this process of conversion of one chair form into another is known as the ring flipping. But during this flipping of one chair form into another, it passes through a higher energy conformation, which we call the twist boat conformation, and in between it also has the half chair the half chair conformation, which converts into a twist boat conformation, and finally it flips into another ring. So we have a chair going through a higher energy conformation and flipping into another chair, right? Now what happens during this flipping, or what is the result of this flipping? We have one chair here and we have another chair. For your understanding, I have drawn all the bonds in different colors, right? So what happens is that when one chair form flips into another, the back of the chair becomes the legs in the second chair. So when the ring flips, the back of the chair in one form is converted or flipped into the legs of the chair. And you see the legs here with brown and red color, they form the back of the chair here in this flipped version. And the seat with this dark blue and light blue color, they are still the seat of the chair. So the back becomes the legs and the legs of the chair become the back. The seat is at the same position. But what other changes are associated with this flipping is that anything or any group that was axial in one chair form now is oriented equatorially in the second chair. So this hydrogen was axial. Here you see it is connected on a carbon atom that is bonded with this other carbons with a pink and a black bond, and you see this pink and black bond here. So this is the same carbon atom as here, which is now the legs of the chair. And the hydrogen that I have shown here is axially oriented, and the same hydrogen here is equatorially oriented. So during flipping, these changes occur. And this hydrogen here with this red and brown bond in the vicinity is equatorially oriented. And when the chair flips, you see this hydrogen is now axially oriented. So all the groups axial in the one chair form are equatorial in the second chair form. All right, so these are some of the changes that occur, and you have to keep them in mind while converting one chair form into another. There is another conformation drawn for this cyclohexane ring, which we call the boat conformation, and you see it looks like a boat. So you can consider it, or you can think of it as a boat. Now this boat conformation is slightly unstable or of higher energy than the chair form. One of the reason is this flagpole interaction between these two hydrogens. You know, flagpole is a pole attached to one or both ends of a boat where the flag is raised to let people know the identity or the identity of that boat from where it's coming. So usually that is the flag of a country raised on a boat. So these two hydrogens are like they are attached to a flagpole. And when you draw this boat conformation, these two hydrogens come closer together in space, and that is where they experience some steric hindrance or interaction with each other. And you know that when there is some steric interaction in a molecule, that brings some sort of instability to the system or to the molecule. And this interaction here is known as the flagpole interaction, because these two hydrogens are actually the flagpoles of this boat. So we call it the flagpole interaction, and that is why this boat conformation is unstable or of higher energy as compared to the chair form. But this is not the only reason why the chair form is more stable as compared to the boat form, or the boat form is less stable as compared to the chair form. There is another major reason associated with it, and let's see what it is. So let's draw or learn how to draw the Newman projection for this chair form. We have already learned how to draw Newman projection for open chain molecules, and we have discussed two examples before in a separate video lecture, and that was of ethane and butane. You can go and see that, watch that video and learn how to draw the Newman projection for ethane and butane. But here we'll be talking about cyclohexane only. So for drawing the Newman projection, you have to view the molecule from an end, and in this case, because it's a ring, we will be looking at it from right through the center of this ring, from here, from this angle. And here you see that these two these two carbon atoms are right in front of your eye, and these two carbons here, they are away from you, or they are at the back of these two carbons. So it's just like in case of open chain molecules, where you have a carbon atom right in front of your eye, and that is your front carbon, and the one that is connected to it through a single bond is at the back, and that is your rear carbon. The front carbon is shown with a dot and the rear carbon is shown with a circle. But because this is a cyclic structure, so we have two carbon atoms here drawn with the dot, or these are the two front carbon atoms shown here. This carbon atom and this carbon atom, they are right here, right? And the two rear carbons are then shown with a circle. So this is one of the circle connected to this carbon atom, and this circle, the rear carbon, is connected to this carbon atom. So we have two dots or two front carbons, and consequently we have two circles or two rear carbon atoms. And now we have to draw the hydrogens attached to all of these carbon atoms. Apart from these four carbon atoms, we have two more carbons, one CH2 here and the other CH2 here. If you look at this CH2, this is slightly lower or oriented lower than the plane of these four carbon atoms, and this CH2 is slightly above the plane of these four carbon atoms. And then we have hydrogens attached to all of the carbon atoms. So let's see how we can draw them. So we start off with this carbon atom, that is the front carbon to the left, this one. It has two hydrogens attached to it, H1 and H2. Now H1 is pointing straight up. It's axial and it's pointing straight up, so you can draw it vertically up from the dot because it's attached to the front carbon. And then we have H2 because it's a tetrahedral geometry, so this H2 will be like moving behind the screen, so it will appear like to the left of your eye. So we draw it to the left and slightly down. You see the orientation, it's moving, or it's oriented pointing down, so we draw it down here to the left. And then to the right of this carbon is this bond, and this is connecting a CH2 to this front carbon. So we draw a bond to the right, and it again is oriented downwards, so we draw a bond here connecting this CH2 to this front carbon. And then we come to this carbon atom, the front carbon, the second one on the right. This has two hydrogens again attached to it, H5 and H6. So H5 again is pointing up, straight up here, and we have H6, equatorial hydrogen, pointing or oriented downwards to the right, right? So H5 is the axial hydrogen, H6 is the equatorial, pointing to the right downwards. And then to the left of this carbon atom, we have a bond connecting this CH2, which was also attached to this carbon atom. So we draw a bond to the left connecting this CH2 to the second front carbon. So now we have three carbons drawn with their hydrogens, and this CH2 has H3 and H4 attached to it, right? Then we come to the rear carbon atoms, the circles, the two circles. So we have the two circles, one here and one here. The circle to the left has two hydrogens attached to it, H12 and H11. And H11 is pointing straight down, it's axial, vertically oriented, so we draw it from the circle vertically downwards, and then to the left, pointing slightly upwards, oriented slightly upwards to the left is H12. And you see H12 is drawn here. It's pointing to the center, but it's drawn from the circle because it is attached to the rear carbon atom. And then we have another circle to the right here, which has again two hydrogens attached to it, H7 and H8. H8 is the axial hydrogen oriented downwards, straight down, so we draw it vertically downwards, H8 here. And then to the right we have H7 slightly oriented upwards, and so we draw it to the right pointing upwards. And if you extrapolate this bond, it will meet center, but we draw it from the circle because it is attached to the rear carbon atom. And then we have this CH2 attached to both the circles, and this CH2 is oriented slightly upwards, so we draw it here with H9 and H10 attached to it. So this is how you draw the Newman projection for the chair conformation. Now, one of the reason I told you for the stability of the chair conformation was that there was no flagpole interaction associated with this chair form, just like the boat conformation. But the second most important reason is that when you draw the Newman projection for this cyclohexane chair form, you see that all the hydrogens are staggered with reference to each other. And you know that when the hydrogens are staggered, they have distance, some sort of distance between them, and the angle between two hydrogens here is 60 degrees. Here we have a 60-degree angle. Here we have a 60 degrees angle. So all the hydrogens you see on the left side and on the right side, they are staggered. So there is no eclipsing interaction between them, or you can say that they are away from each other in space. And that is why this cyclohexane chair form is more stable because of this main reason. Now we come to the boat conformation, and let's see if we can draw a Newman projection for it. So again, we weave it from this end, and just like the chair form, we have the two dots. So we have these two carbon atoms right here, the two dots, and then we have the two circles. So we have the two circles here, the rear carbon atoms. So we draw it in the form of a circle. And then you draw the hydrogens. So we have H2 and H1 attached to this carbon atom, the dot on the left hand side. So we have H2 straight down and H1 pointing upwards to the left hand side. This is equatorial, and H2 is straight down, it is axial. I have drawn it slightly tilted just to keep it away from it, so as to let you know that these are two hydrogens. If you draw it straight down in front of this H11, that you won't see both of them. So I've just drawn it in tilted form. Otherwise they are right in front of each other, eclipsing each other. And then the dot to the right has two hydrogens, H5 and H6. H6 is pointing down, straight down, and H5 is to the right, pointing upwards, which is equatorial. And then the two circles have H11 and H8 pointing straight down. So this left hand side circle has H11 pointing straight down, and the right hand side circle has H8 pointing straight down. And it has the left hand side circle has H12 pointing to the left, slightly up, equatorial, and this circle has H7 pointing to the right and slightly oriented upwards. So this is how you draw the hydrogens on these four carbon atoms. And then we come to the final, the two CH2s. You see, this CH2 is now oriented slightly upwards with reference to the plane of this molecule, or your eye line. So we draw it upwards with this blue line. So this is the blue CH2, which is right here. And also the CH2 attached to the circles is slightly upwards, pointing up, drawn with the red bonds. So you see the red CH2 here with their corresponding hydrogen atoms. Now, when you draw the Newman projection, you can see that all the hydrogens, all the 12 hydrogens are eclipsing each other. They are right in front of each other. And apart from the flagpole interaction between this H9 and H4, which makes this boat conformation relatively unstable, the other main reason is that all the hydrogens are eclipsing each other. And you know that when the hydrogens or the groups are eclipsing each other, that means that the groups are closer together in space, and that brings some sort of instability to the molecule. So that is made clear when you draw the Newman projection. So you should know how to draw the Newman projection for the cyclohexane chair and the boat, and that will make clear which one is more stable and which one is relatively less stable. So this was all about cyclohexane. We'll discuss some more topics in detail in the upcoming lectures. So stay tuned. Thank you so much.